name's Carl Schmidt. I'm a researcher at a laboratory called LATMOS in Paris, France, and I study planetary atmospheres there. So the Jupiter system has the most massive magnetosphere we know of. It's vast. It's one of the largest objects in the solar system. And all of the plasma content, for the most part, in Jupiter's magnetosphere is supplied by this moon, Io. The Io plasmatoris, as we call it, is an object that wobbles around Jupiter. And it wobbles because it's trapped in Jupiter's magnetic field, which is not directly centered on Jupiter, and it's not aligned with Jupiter's spin axis. It's tilted. So the magnetic rotation axis is about 10 degrees off of its spin axis. And this happens on the Earth too. Magnetic north is not the same as true north. But Jupiter's magnetosphere is so powerful that it takes all of this material and throws it by centrifugal forces through fast rotation all the way to the edge of where it can lie along the magnetic fields. And then that tilt sort of wobbles the plasmatoris back and forth. The original source for all of this is Io's volcanism, and that is mostly sulfur and oxygen. Sulfur dioxide is coming out of the volcanoes, trace amounts of sodium and potassium chloride, which is just table salt. And that material forms neutral clouds around Jupiter and this massive plasma structure that we call a torus. You can study this with small telescopes in a very interesting way, in that you get to monitor what is the atmospheric loss rate and loss mechanisms working on Io, where the material originally came from that moon. So I'm showing on this slide two different images, and one of them was a movie made by the Cassini spacecraft, which is plunging into Saturn in the next couple of months, wrapping up a very long and successful mission, which has taught us a lot about the Saturn system. On its way to Saturn, the ultraviolet spectrograph on Cassini stared at this Io plasmatoris for months and months. It's a small telescope, but it operates at ultraviolet wavelengths. And even though we don't collect so much light here and there, if you add it up over months and months, you can learn quite a bit. This scrolling tick mark that's moving above and below that image is Io's location in the plasmatoris. And we can see when Io moves through one of the edges where we see the most emission because of the largest column going through the object, it gets a little bit brighter, and the plasmatoris is always brighter on the dusk side. And those are things that we want to understand, why do they happen? Why does Io's location change the brightness of the plasmatoris? Why is the plasmatoris brighter on one side? In the optical, Io is shiny, just like it is in the infrared. That reflected light off of the surface contaminates the images, where it's not as much of a problem in the ultraviolet, where the albedo, the reflected light from the surface, is about 1 or 2%. You can study this in the visible by looking at emission from sulfur. There's sulfur dioxide coming from these volcanoes, and that sulfur dioxide gets ionized and recombines into neutral sulfur, or gets ionized into different charge states of sulfur and oxygen. And ionized sulfur is trapped in the magnetic field. This is a great way to image a magnetosphere. We talk about dynamics happening in magnetospheres and how plasma is behaving, but taking a picture of it is a pretty novel and interesting thing to do that we can learn a lot from. And it's especially interesting to do it at Jupiter, where you can actually study it over long time scales, monitor its behavior, how its behavior changes with volcanoes on Io, and with different solar wind conditions, to learn about how material spreads through a magnetosphere, and how that material eventually can cause things like aurora and things like plasmoids bubbling down the magnetotail. There's all sorts of interesting physics that happen to those ions. So being able to actually take a picture of them is a really interesting thing to do from a science perspective. So to study these emissions at Jupiter, there's an observatory in Texas, in West Texas in the US, that has two very small telescopes that are constantly looking at Io and these emissions. One of them is a 40 centimeter Cassegrain telescope, and it feeds an imaging spectrograph, an image slicing spectrograph, and I'll talk about what that is and how that works a little bit later on. But one of the most useful instruments is actually only a 10 centimeter aperture telescope. It operates as a coronagraph, and a coronagraph is where you use a mask to block out some bright target to image the faint things around it. So the great example is if you want to look at the sun's extended atmosphere, you can just use a filter to stop down the light by a factor of 10,000 or more, and image the faint material that's right around it. And so we're operating that 10 centimeter telescope as a coronagraph to look at the extended atmospheres of Mercury and Jupiter and comets. So in order to isolate just one emission, we need to use narrowband filters. And we need to understand the properties of those filters very well. Because light is coming in not at a direct angle, we're looking at a wide field of view, like we often are with small telescopes. The light can intersect our filter at different angles, and that changes the optical properties of the filter. So we need to cancel out those effects. And we also need to remove all kinds of starlight. So the trick here is to take Jupiter's reflectivity, this I over F, at two different filter bands, and multiply that by the integrated bandpass that is underneath the filter, times what's coming from the sun. If we then take a filter which is on a certain emission feature and off a certain emission feature, we can scale and divide those two. And then you can use the background stars in order to figure out the absolute brightness. You can calculate the sensitivity that we are, where how many photons correspond to one count on our detector. Earth has sodium in its upper atmosphere. It comes from meteorites burning up around 100 kilometers in a region called the mesosphere. And so we actually have to look through a cloud of sodium emission in our atmosphere in order to see anything from objects in the solar system. There's a constant background that needs to be subtracted in order to look at just the light from an object like Io. Once we include all of those effects, the emission that we see from sodium around Jupiter extends for hundreds of Jovian radii. It's one of the largest objects in the solar system. It's a very diffuse cloud of sodium spreading its way throughout the system of Jupiter, where it escapes completely. These atoms are on escape trajectories, and they form a diffuse cloud which extends hundreds of Jovian radii, but sort of falls off exponentially. There's pretty good evidence that that sodium cloud is originally sourced from sodium chloride, table salt, which is a trace component in the volcanic plumes. So it's mostly sulfur dioxide, but some NaCl, sodium chloride, can get broken apart by sunlight and ionized. So you would form a molecular ion, NaCl+, from a low energy photon hitting that table salt. That electron cloud that's around Jupiter, the Io plasma torus, can then bump into a molecular NaCl+ ion and break it apart. And that gives you a fast, energetic neutral chlorine and neutral sodium atom, which then fly off into space and escape Jupiter completely. So there's good reason to expect that this distant sodium cloud would correlate and scale with what the volcanic activity is on Io that we're measuring with another small telescope independently. And if we look at periods where Io is very active in the infrared wavelengths, they tend to correspond to an active sodium nebula from all of this material escaping. And then if we look at the plasma torus and how things react to a volcanic eruption, we see all this chemistry going on, where there's a certain envelope for how sodium increases over, it can be month timescales, which is different from the envelope of how different charge states of sulfur increases and how the aurora of Jupiter changes in its brightness. And those are being monitored constantly now by a Japanese spacecraft called Hisaki, which is for more than 7 years consistently just monitoring the Io plasma torus and Jupiter's aurora and material that comes from Io whenever Jupiter is visible in the sky, not too close to the sun. So sodium is a particularly attractive thing to look at with small telescopes because it's unusually bright. It has this property where sunlight can be resonantly scattered off of sodium atoms. So sunlight comes in, excites an electron orbiting a sodium nucleus into an excited state, and then that excited electron drops back down and de-excites. And it's almost like the sunlight was reflected, but it actually corresponds to a specific wavelength, a transition in the atom. One form of small telescopes is just an all-sky camera, a fisheye lens that images the entire sky. And you can put filters to just look at sodium in the optical path in order to isolate just a specific frequency where sodium atoms are bright. When that was first done to study structure in Earth's upper atmosphere, where all of this meteoritic material is causing sodium emission, a little spot was often seen at new moon, and it wasn't clear exactly what that spot was for a long time, but it was actually determined that it was the atmosphere of the moon at sodium wavelengths being swept past the Earth and forming a sort of spot in the sky which is directly opposite of where it's being created. So this is called the lunar sodium tail, and it's especially interesting because the atmosphere that's being lost from the moon is being pushed away from the sun, but it's also being pushed past the Earth. And when it gets pushed past the Earth's gravity focuses the moon's atmosphere, just like a lens focuses light. And it bends the trajectories of those atoms in order to give you this bright spot where things come into focus. And that bright spot is what's being observed in this small all-sky camera looking at sodium. So we can not only use the all-sky cameras for their traditional purpose of studying Earth's upper atmosphere, but they can also study how the moon's atmosphere is being lost after it gets processed by the Earth.